with transformations, and today we're going to be looking at graphing each function and describing how the common or parent function is actually moved in order to become the function that we graph, okay? Now I say moved, but really I'm going to be talking about transformed, okay? All right, we're going to start with this example. P of x equals the absolute value of x plus 5. First thing I need to do is identify my common function. So the common function that I'm playing with in this case is y equals the absolute value of x. The absolute value of x, you can see the absolute value symbols right here, and you see the x, so you know you're not dealing with a square root function or a square function or a cube function because you don't have any of that information. But you definitely see the absolute value symbols, so we are going to manipulate y equals the absolute value of x in order to get y equals the absolute value of x plus 5. So do you know what this function looks like? Let me see, that looks a little crooked, doesn't it? This function, y equals the absolute value of x, looks like it is in the shape of a V, cutting right up through quadrant 1 and quadrant 2 perfectly, 45-degree angles out from both quadrants. Just make that a little bit nicer for you. Y equals the absolute value of x. So this function that we're going to graph is going to have that V shape with that vertex and that cusp at 0, 0. And I don't know if you've heard the word cusp before, but a cusp is a sharp point. It's not nice and smooth, it's sharp. So we definitely have a cusp at 0, 0 with our common function of y equals the absolute value of x. Now we're going to do a little mapping and pick points and see about graphing this p of x function, which is the absolute value of the quantity x plus 5. So I am going to mark my x-axis here, mark my y-axis here. Guess I'll go a little further. There we go. So if I had input output, again, this is a nice mapping. I like to do my mappings. P of x equals the absolute value of x plus 5. And just make sure that is my function. Yes, indeed it is. So I want to pick a number, plug it in, and see what I get out of the deal. So I typically like to put my 0 in. If I put a 0 in, I go 0 plus 5, which is 5. Take the absolute value of that, and the absolute value of 5 is 5. So 0 is paired with 5. So I need to come up here and mark 0, 5. 1, 2, 3, 4, 5. And always label. Every single time you put a point on a graph, you follow it with open parentheses, x coordinate, comma, y coordinate, close your parentheses. Now let's pick another number on my graph here in my domain. I'll pick a 1 or a 2 or a 3 or whatever you'd like to pick. Let's just go ahead and start with a 1. 1 plus 5 is 6, and the absolute value of 6 is 6. So 1 is paired with 6, which means my input-output combination, or my xy coordinate point that I need to graph, is 1, 6. Here's 1, 6. Okay. If I picked a 2, which I suppose I will, if I picked a 2, 2 plus 5 is 7, the absolute value of 7 is 7. I think you can kind of see a pattern there already, so it'd be a waste of time to keep going. But I will plot 2, 7, 2, 7. Alrighty. Typically we want at least 3 points in our graph, and then we have 3 points, but we're going to want a little bit more than 3 right now, because if you see those 3, you're going to think that this function's linear. I hope you don't. I hope you realize that there's an absolute value thing happening in your function, so therefore p of x has to look like your common function somehow, with some kind of a twist or movement somehow with this V shape. So I don't have a V shape yet. And I kind of get the idea that this is just going to get higher and higher and higher the more I increase my x values. So I need to go the other direction and see what's happening over in quadrants 2 and 4. See what's happening 2 and 3. See what's happening over here. I'm going to put a -1 into my function. -1 plus 5 gives me 4, and the absolute value of 4 is 4. So -1, 4 is a point that I should put into my graph here. -1, 4. And I'm going to erase a little bit of my axis so I can write -1, 4. There we go. Now if I pick -2, -3, and so on, I'm going to see that these numbers continue to decrease, which is good. But what is a really good friendly number that I should put in here right now to try and get this job done and see what's going on? And that number would be a -5. Put a -5 into this function and you'll see that this will give me a 0 out of the deal. So if I put a -5 in here, I'm going to come up with 0. So anytime you get an absolute value function, actually, I would like for you to take this thing that I call my oogie boogie. Take your oogie boogie, or the quantity that's inside of your absolute value symbols, set it equal to 0, solve for x, and make sure that that's a value that's going to go into your domain. Negative 5, comma 0. 1, 2, 3, 4, 5, negative 5, 0. Because what you do right here is you find the x coordinate to this vertex, to this cusp. So x equals negative 5 is the x coordinate of, I was going to say your, as if you own it, of the vertex. Now, sometimes there's more information than just y equals the absolute value of x plus 5. There might be something on the outside here, there might be something on the outside here. So you really do have to take the negative 5, put it into the function, and see what you get out. Because if you have something else manipulating your function on the outside, some kind of a vertical shift up and down, it's going to change this answer. So don't just think that whatever goes in here, your negative 5, that makes 0 inside your absolute values, don't think that that's going to be paired with 0 all the time. It isn't, okay? So just to point that out to you a little bit. So negative 5, 0 is a point on my graph. Let's go a little bit further to the left, because I know that you know that absolute values affect negative numbers, but they don't affect positive numbers. So if you have a negative number under your absolute value, or inside your absolute value, the absolute value function will take that negative number and turn it positive. But what does the absolute value do to positive numbers? Leaves them alone, right? So that's why all of our positives are still going to positives here. We want to get a few negatives and see what else is happening. Also explains why setting this boogie boogie equal to 0 is really important, because 0 is the number that's in between your positives and your negatives. So you really want to see what's happening if you're picking values that are on either side of negative 5. So how your function is going to change from your negatives to your positives. So let's pick negative 6, you'll see what I'm talking about a little bit. I put negative 6 into my function as x, and I add 5. That gives me the absolute value of negative 1. The absolute value of negative 1 is positive 1. See how that one's changing. So I have a positive 1 here. I need to plot the point negative 6, positive 1. Negative 6, positive 1. And I think now we're kind of seeing the function turn around. This function is going to decrease until it hits its vertex, and then, well, I shouldn't say that actually, but because from the vertex forward, we always look at a graph from left to right. So this function from negative 5, 0 is increasing to the right, but from the left, coming towards negative 5, the function will be decreasing. So we can pick another number, just negative 7 or something, put negative 7 into your domain, and figure out what range element pops out. Put a negative 7 into your function. Negative 7 plus 5 is negative 2, and negative 2's absolute value is positive 2. Okay, so negative 7, positive 2, negative 7, positive 2 is up here. Actually, it's probably down just a little bit. And my absolute value function should look like this. If you miss a point, just kind of like make it look good. Okay, the slant that you have on one piece of your absolute value function should be the same slant that you have on the other piece. Never will one side be slanted, steeper or not so steep compared to the other. They're going to have the same exact slant. I would say one will have a negative direction, one will have a positive direction. All right, so this is the function p of x equals the absolute value of x plus 5. I want you to compare that to y equals the absolute value of x, the parent function that stems it. What do you see? I'm hoping that you'll see that this parent function is moved to the left by 5 units. And that seems really weird. I know it seems weird that you're looking at the absolute value of x plus 5, and yet this function, this p of x function, is 5 units to the left of y equals the absolute value of x. And that's going to be the trickiest thing that's going to happen to us probably at all, is that when we see this plus 5 embedded inside the common function, we're going to have to counteract it and do the opposite of what you see. So an x plus 5 inside your absolute values takes the absolute value function and shifts it to the left 5 units. This is not a shift to the right 5 units. This is a shift to the left 5 units. And in a way, if you want to think about it, what I think of is that if I wanted to get back to my original function of y equals the absolute value of x, I would have to put x values into this function right here that are 5 units smaller, because I know they're going to have a plus 5 attached to them. So I need to counteract the fact that 5 is going to be added to my x before I start, which means I need to shift my whole entire graph 5 units smaller, which 5 units to the left. So let's get that written out as our description. So we are going to describe this graph of p of x. So p of x equals the absolute value of x plus 5 is y equals the absolute value of x shifted where? Shifted left 5 units. And I know you're questioning, well, what if it was going the other way? Would it go to the right? And that's what we're going to do with the next example. So yes, absolutely right. Okay, this is my graph. Can't get in my answer box, you little devil. Okay, coming over here, down. And this is everything I was asked to give. I was asked to graph this p of x equals x plus 5, labeling at least 3 points, okay? And describe how the common function is moved in order to create the new function that I graphed. All right, and this is y equals the absolute value of x is moved or shifted 5 units to the left. All right, our next example will be example 4, and we will be going with k of x equals the quantity of x minus 3 cubed. Okay. Quantity x minus 3 cubed. So this is my common function. Can't write. So what is my common function? It's not the absolute value of x anymore, because we don't see absolute values here. It's not y equals x squared, because I don't see a squared. Yeah, you're right, y equals x cubed, because that's exactly what I see. That's the big thing that's happening in this function right here. So y equals x cubed is the common function that is going to become manipulated in order to give you the quantity of x minus 3 cubed. All right, do we know what this looks like? I hope you know what it looks like. You should. Okay, we're kind of steep here, but we're up in quadrants 1 and 3. Y equals x cubed starts low and ends high. It's a cubic function. It's got a little whoop whoop thing going on in the middle of it. We've talked about that. It's a change in concavity. We're going from concave down to concave up. And we'll just skim over that concept right there. So now I want to graph y equals x minus 3 quantity cubed, which means I need an xy axis. And I know y equals x cubed is like up and down kind of somewhat. So I want to give myself enough room going up and down. And I want input and output. And this is k of x equals x minus 3 quantity cubed. Now what number would you like to put in there? And I know most people are going to say 0. They want to put a 0 in, so I will put the 0 in first. When I put 0 in here, 0 minus 3 is negative 3. And when I cube negative 3, I get negative 27. So negative 3 cubed is negative 3, negative 3, negative 3, all multiplied together. That's a negative 27. And I just don't feel like graphing 0, comma, negative 27, because it would be down here someplace, all the way down. And it's my discretion. If I choose not to plot that point, then I just have to go dig another point out. So I'm going to do what I did with the absolute values over here, and I'm going to take my oogie boogie, so to speak, my x minus 3, and I'm going to set it equal to 0. And I'm going to add 3 to both sides of my equation. This gives me an x equals 3. This is the number that I definitely want to play with, because something's going to happen there. So if I put a 3 into my function, 3 minus 3 is 0. You cube 0, and you get 0. So 3 comma 0 is my input output, which turns into my xy coordinate point I need to plot. So 1, 2, 3, 0. what's going on. So if I pick 4, 4 minus 3 is 1. You cube 1. 1 times 1 times 1 is 1. So the xy combination I need now to graph is 4 comma 1. So 4, 1. Let's pick 5. 5 minus 3 is 2, and when you cube 2, you get 2 times 2 times 2 is 8. So 5 comma 8. And I might almost say, no, I don't want to do this, but I'm going to hit this one. Here's 5, and then 1, 2, 3, 4, 5, 6, 7, 8. 5 comma 8. It's up there, but it's not up too high. Remember I told you I wanted some length to my function because I knew I was playing with x cubed. And that's knowing what you're doing ahead of time, too. All right, now let's go to the other side of 3. What point is to the other side of 3 that would be nice to plug in? Let's try it. 2. Take 2, subtract 3. That gives you a negative 1. And then you need to cube negative 1. When you cube negative 1, you get negative 1. Because negative 1 times negative 1 times negative 1 is negative 1. So 2 comma negative 1. And I'm going to erase just a little section of my axis so I can label my point. And I'm going to try another point to the left a little bit. I'm going to try 1 as my domain element here. Take 1, plug that into my x as my input. 1 minus 3 is negative 2. You cube negative 2, that's negative 2 times negative 2 times negative 2. Gives me negative 8. I can kind of see a pattern going on here. So 1 comma negative 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, negative 8 would be way down here. But can you see what's going on with your graph? Can you see that what you're going to get is something that looks like that function up here, your common function? It's important to pick more than 3 points though, because if you only pick these 3 points, you're going to be talked into the fact that this might be linear. And you have to pick at least 3 points. But you also have to know that this function up here, this cubic function, is not linear. There's no way I'm writing that in y equals mx plus b form. So do not draw me a linear function if the function itself can't be linear. All right, so this has got a little whoop whoop going on, and my little point where I'm going to have that little whoop whoop is right there at 3, 0. So we're going up, kind of steep, and we're going to go down, kind of steep. This function will cross the y-axis, but it'll take a little while to do it. But it definitely will cross the y-axis. Matter of fact, if I put x equals 0, the function crosses the y-axis right there at negative 27. So we know what's going on. All right, I'm going to erase my mapping and write my statement. Little arrow right there. All right, so k of x equaling x minus 3 quantity cubed is y equals x cubed shifted where? I'm going to say right 3 units. Okay, just take this y equals x cubed and shift it to the right 3 units. You get good at transformations, and you don't have to plot points anymore. You can just take a look at the origin of the function that you want to graph, compare it to your common function, which you know what looks like off the top of your head, move it wherever it tells you to move it according to your laws and rules for transformations, and then you get your answer. You get your final product of your graph. All right, this box is going to look a little weird, but it's going to look, so we're going to do it. My graph is here. I want to catch all of it. Here, I don't need my common function, so I'm going to go out of the way a little bit. And give you something like that. All right, so I have my graph and I have my common function. And now I have another rule. And I want to talk about that word executed, okay? Let's get back in here before we hit our rule. This particular type of transformation that we have is executed before, or it is completed or whatever, before the common function is executed. So for instance, when I took my 2 and I put my 2 into this function of the absolute value of x plus 5, didn't I add the 5 before I executed the common function, which is the absolute value idea? So if I add the 5 first, and then I execute the common function, that means the 5 is making a change to the x, not the y. So everything here with these two transformations is definitely affecting the x, unlike the previous video where we affected the y. So anytime the change in your common function occurs before the common function is executed, you're changing your x. If the change occurs after the common function is executed, you're changing your y coordinate. Same thing over here. When I plugged a 5 in, I subtracted 3 first from the 5, so I changed my x before I cubed. That means that the whole change in the transformation is going to occur to the x coordinate, not to the y coordinate. Right? So when you change a function, when you change a common function, before that common function is executed, the change occurs to the x coordinate. And when you change a function after the common function is executed, the change occurs to the y coordinate. And sometimes it occurs to both of them at the same time, so we're going to get messy on this. All right, let's come over here to our rule. And let's just give a couple of these things. Let me see here, like I did in the last video here. So I'm going to say y equals f of x plus c. Notice I'm going to put the plus c inside the set of parentheses, just like it's inside the set of parentheses or inside your grouping for both of these examples. I don't need parentheses here, but if I put them there, that'd be okay, because this is already grouped with my absolute values. These symbols are actually, I don't need parentheses because they're kind of grouping this x plus 5 together already, and that's all parentheses do is group things together. So obviously x plus 5 is a quantity or an oogie boogie that the absolute value is being applied to already. So this 5 is affecting this x. This 3 is affecting this x. Actually, it's a negative 3 affecting this x. So my rule is going to look like y equals f of x plus c is f of x shifted where? This time it's not up and down, this time it's left and right because you're affecting x and x goes left and right, so you have to make that change in that direction. So x plus c would be indicated with example 3, and with example 3 we saw x plus 5, so we move 5 units to the left. So over here, when you see a plus c, you move left 5 units. I'm going to write left down here. Left. And why would I write 5? Because this is my general rule. I don't want to write 5, I want to write c units. And again, now instead of left, I'm going to say right. So y equals f of x minus c is f of x shifted right c units. Okay. Now instead of saying left and right, what word could I come up with? Horizontally. So these two rules here, these are for horizontal shifts. And I can put it together and merge it as one rule if I'd like. And I could say y equals f of x plus c is f of x shifted, and this time I'm not going to say left or right, I'm just going to say horizontally c units. Now if the c value is positive, then everything will say x plus 2, x plus 3, x plus 5, x plus whatever, and we'll be shifting to the left. If the c value is negative, then it'll turn that plus sign into a minus sign, and this will look like x plus a negative 2, or x minus 2, or x minus 3, or x minus 4, and then we shift to the right. I like to put them individually because I like to see the left and the right idea instead of just horizontally. I want you to know which one goes left, which one goes right. But if you do look it up